Welcome to College Algebra. In this lecture video, we will begin to talk about introductions to polynomial equations and graphs. So the lecture video for 4.1 series, we will mainly focus on a little bit about the polynomial equations and the graphs. So let me kind of start you off with all the ways of finding the zeros. So the 4.1, 4.2, 4.3, many things we talk about has something to do with finding the zeros of a polynomial function. So one of the ways I showed y'all before is by factoring. If I have a polynomial such as x squared minus 4 equal to 0, okay, we can actually solve by factoring. So x squared minus 4 is a difference of square, so we can say that's x plus 2 times x minus 2 equal to 0. So once I factor them, we will set each factor equal to 0. So my zeros of the polynomial is -2 and +2. Now there were questions before asking what is the x-intercepts of this parabola. So that would be -2, 0 and 2, 0. So the techniques that we find the zeros or finding the x-intercept is the same, but the answer is actually different. These two answers is the zeros of a function, and these two answers are the x-intercepts, because there will be times where I don't have any x-intercept, but I can still have the zeros of the function. Alright, I can also find zeros by graphing. Remember, if we do it by graphing, what we'll be looking for is basically the x-intercept. So for example, x to the second power minus 4, okay, the zero of my polynomial is where the x-intercept occurs at, so that will be -2 and 2. Okay, so if I will change it to x squared plus 4, then this problem is no longer able to solve by factoring. And if I graph it, I don't have any x-intercept as well. But still, I have zeros of the function. I just do not have the x-intercept. Okay? Let me go back. There will be times when the function does not cross over the x-axis. Okay? Okay? When the time, when there is times, the function does not cross over the x-axis, we don't have any x-intercept, but we do have certain types of zeros. Okay, and we will talk more about that in a different lecture video, the different types of zeros we have. One thing to keep in mind is x and y-axis are real number lines. Okay, only real numbers exist on the x-axis and y-axis. So when we run into zeros that are not real, then it will not show up here. Alright, so another way to find the zeros, okay, you will have to stay tuned. Allow me to show you more concepts before we can comprehend the ultimate way, Mr. Chen's ultimate way to find the zero. So let's kind of do this from the very beginning. Okay, introducing what a polynomial function is. A polynomial function p, we use the letter p for polynomial, is given by this formula: a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 power plus ... and then a sub 2 x squared a sub 1 x to the first power. So when we have a polynomial function, all the coefficients are real numbers, and all the exponents got to be whole numbers as well. Okay, so exactly what is all these a sub n minus 1? Those are your real number coefficients. I use a different subscript just to indicate just indicate different coefficients we can have. All right, every one of these terms using the same variable. So the n minus 1 are your exponents. Okay, x to the first power. Okay, so a sub n, a sub minus 1 are coefficients. Okay, n minus 1 are your exponents. Okay, polynomial, we normally express them as in descending or ascending order on the exponents. What I mean by that is, if I will start you off with n equal to 5, so that means x to the 5th power. The next one is n minus 1, which is 4. The one after that got to be 3, then 2, then 1, then the last one is actually x to the 0 power. Because as you can recall, anything to the 0 power is equal to 1, and 1 times whatever coefficient that is still that coefficient. Okay, so we generally express polynomial in descending or ascending order on the exponent. What is so-called the leading term is referring to the term with the highest exponent. Okay, so that term got to be at the very beginning. So for right now, my leading term will be a sub n x to the n. Leading coefficient is referring to the coefficient of the leading term. When I use the wording degree of the polynomial, that's referring to as the highest exponent. So when I look at a polynomial, I got to find the degree of the polynomial, so I know what the leading term is, so I know what the leading coefficient is. Okay, now if the leading term for a polynomial function simply is going to be x to the 0 power, is referring to as a constant function. So if I would just simply say f of x equal to like an 8, that 8 is actually 8x to the 0 power, because that would be 1 times 8, which is still 8, and that would be considered as a constant function. And as we previously mentioned, constant functions is basically a horizontal line. Alright, if the exponent of my leading term is to the first power, we call those a linear function. To the second power is quadratic. To the third power is cubic function. To the fourth power is called a quartic function. Okay, so we mentioned all these type of functions previously before. So most of y'all kind of know what they're already called. But here I'm just kind of formally organizing them a little bit for you. Remember now, right, this particular section here, all these are polynomial functions. So in this video, we're not mentioning anything like a square root function, or absolute value function, or things like rational functions. Alright. The idea of leading term test. Maybe I should have highlighted this word too. Leading term test. Leading term test actually will tell you the ending behavior of your function or your graphs as your x value keep on going to the right, or as your x value keep on going to the left, negative infinity. Now, why is it important to know this leading term test? Because the ending behavior tells you what the graph, okay, would not curving back towards the x-axis. Because if you have a graph way down the road to the right side, if you curve back towards the x-axis, that can potentially give you another zeros, okay, way beyond your graphing calculator screen. Okay, so in a way, by knowing the ending behavior, it guarantees that the graph will not curve back. So if a sub n x to the n power is your leading term, then the ending behavior as your x keep on going to the right or left can be described in these 4 pictures. If n is even, Okay, that means the exponent, n is the exponent. If your exponent is even, like a square, x to the 4th, x to the 6th, where s of n is greater than 0, and we mentioned greater than 0 means positive, just another way of saying positive. So if the exponent is even on the leading term, and the leading coefficient is positive, it guarantees that once my graph go into infinity, my y values, okay, or my graph will keep on going up, 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 up. Same thing on the other side. As x keep on going to the left, the y value is increasing. Okay, it's keep on going up, 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 up. The scribble part right here in the center is what's going on around the x-axis. Okay, we'll talk more about this part. If the exponent is even again, but this time my leading coefficient is negative, just like a parabola open downward. Once it point downward, you will continue to decrease. The y value will continue to go more negative on both ends. Alright, if I have something like a cubic function, if n is odd, if the leading exponent or the degree of a polynomial is odd, but the leading coefficient is positive, then the right side keep on going up, up, up as going to infinity. The other side, as x keep on going to the left, my y value is decreasing. Alright. If I got a cubic function or x to the 5th power, but this time my leading coefficient is negative, this time the left side, as x go into negative infinity, the y value goes up, 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 up. As x go into positive infinity or go to the right, my y value goes down, 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 down. Okay, get more negative. Alright, so that's the different types of ending behavior we are going to see. So for example, consider this parabola. Find the degree of the polynomial. So the degree of a polynomial is referring to the highest exponent, which in this function would be 2. Because now you will notice that the degree of polynomial tell you who is the leading term. So the leading term is 9x squared. So the leading coefficient is a coefficient of the leading term, which would just be 9. Alright, so this one, even exponent, positive leading coefficient, that would be this one right here. So both sides will go up as x go to the right, go to the left. So describing the behavior of the graph. So as x go into positive infinity, keep on going to the right. Alright. My y value is also going to go to infinity. Keep on getting bigger and bigger and bigger. So as x go into negative infinity, my y value is also getting bigger and bigger and bigger, going to infinity. Alright. Now this one, for example, the degree of the polynomial the highest exponent we see in this polynomial function is a 3. So that will tell me the leading term is going to be 6x to the 3rd. So the leading coefficient would be positive 6. Alright. So odd exponent, positive coefficient on the leading term, that will give me this graph. So the right side goes up, the left side keep on going down. So as x keep on going to the right or infinity, my y value is keep on going up to positive infinity. As my x value keep on going left, remember this side is left and down, my y value is going to negative infinity. Okay? Alright. Let's take a look at the idea of even and odd multiplicity. Even and odd multiplicity on a factor of a polynomial determines whether the function will cross or you will turn at the x-intercept. Okay? You'll determine the behavior of your graph. What is it doing around the x-axis? So if x minus c to the k power is a factor where k is going to be greater than or equal to 1, okay, so what happened is if this exponent is odd, remember now 1 is an odd number. If the exponent is odd, then the graph will cross over the x-axis at that number c comma 0. So using this one for example, okay, the even and odd multiplicity is referring to the factors of the polynomial. So if you look at the factors of my problem earlier, x squared, maybe I should also copy down, but nah, I'll copy it on the problem up here. X squared minus 4 equal to 0. Well, I factor x squared minus 4. Okay, these two are my factors. So my x minus c, okay, is what's in the parentheses. So if you look on the exponent of my two factor, both of them are 1, which is odd. That means my graph will cross over the x-axis at these two numbers, negative 2, 0, and positive 2, 0, just like what you see here. Okay. When we add up the multiplicity, that will equal to the degree of the polynomial. So at the same time, the exponent, the degree of the polynomial being a square, also telling you at most how many zeros you should have. We should have at most 2 zeros. Okay? Now let me give you this example. If I have a trinomial that says x squared plus 4x plus 4 set it equal to 0, and if I factor this thing, normally for trinomial, student will say, okay, that is x plus 2 and x plus 2, because 2 times 2 on the back give me my 4. If I add them, I will actually end up with the middle term, which is positive 4. So by looking at it, you notice that the exponent on the factor is 1 and the 1. But since these two factors are exactly the same, then this is basically saying this x plus 2 whole thing squared is equal to 0. So technically x plus 2 set it equal to 0, x is equal to negative 2, so is the other one. So but these two answers are exactly the same. So that tells you that when the exponent on the factor are even, then the graph is actually tangent to the x-axis. What that means is it will actually turn at the x-intercept. These two are the same x-intercept. So I still have 2 zeros. It's just the 2 zeros are exactly the same because the multiplicity is even. So if I will graph you this function, x squared plus 4x plus 4 is a parabola, it actually turns right there at negative 2. It never cross over. Okay. And it matters too. It matters because if my parabola crossed it, then it can potentially cross back to the x-axis again. So would it cross back or would it not cross back? And that's where the leading term test comes in. It ensures that once your y value going up or down, it's not gonna curve again back towards the x-axis. Okay, so by the leading term test, okay, positive leading coefficient, exponent is even. So once I see that this side, once it goes up, it will never curve back towards the x-axis. The other side will also goes up as x go into infinity or negative infinity. All right. So even though my degree of the polynomial is 2, I'm supposed to have 2 zeros or 2 x-intercepts. But the 2 is simply implying you will have at most 2 zeros. So in this case, I actually have 1 0 here. And the reason why I only got 1 0 here because my 2 zeros are exactly the same. Alright, so let me give you this example here. Okay, finding the zeros of each polynomial function. We can actually graph this function. We will actually see the zeros. But I'm going to show y'all show y'all how to do this problem by thinking about the even and odd multiplicity. And this problem is factorable. So if I perform a factoring by grouping, the greatest common factor between the first 2 terms are x squared. And I should have x plus 7 in the parentheses. Between the last 2 terms, I got to factor out a negative 4. Because that will make my 2 parentheses the same, x plus 7. So between the 2 terms, the greatest common factor is the x plus 7. So if I factor that out, I get x plus 7 times x squared minus 4. And x squared minus 4 can be factored again. That will give me x plus 7 times x plus 2 times x minus 2. Alright, so I supposed to set my y equal to 0, because when we're trying to find the zero of a function, who is 0? The y is 0. So let me add in my y equal to 0 here. Set each factor equal to 0. So my x is equal to negative 7, my x is equal to negative 2, the other 0, x equal to positive 2. So what would the graph be doing at these 3 0 or x-intercept? Well, the multiplicity is 1 1 1, so that means the graph will cross. So if you don't believe me, let's graph it. You'll cross over x-axis 3 times. Remember now, this is odd. Okay, this is an odd degree. Okay, leading coefficient is 1. X to the third plus 7x squared minus 4x minus 28. Okay, so no surprise about the looks. Whoa, what's going on here? Alright, let's go back up. The right side is supposed to go up, left side is supposed to go down. So this picture, excuse me, let me go back here to this page. This picture is actually supposed to be this. Okay, that's x-axis. Okay, that picture is supposed to be something a little like coming from negative infinity down here. You can cross at negative 7, turn back, cross over at negative 2, and then eventually have a y-intercept way down here at negative 28. How do I know? Because y-intercept x equal to 0. So if I put 0 0 0 here, the y-intercept will be way down there. So I'm just gonna kind of draw a little bit smaller. It's gonna curve back towards the y-intercept and then cross over again at positive 2. So you cross over at 3 different points. Okay, that's what the even and odd multiplicity tells us. The behavior of your graph, or what is it doing around the x-axis? Does it cross or does it turn? All right. we will end this short video right here. Thank you for